let's think, what about solid material? Because the class is more concerned with solid material. Do we have a way to measure, or at least from a first principle, to understand the energy for a crystalline surface? Crystalline material, if it's a surface, what would be the theoretical energy? How do we understand? So let's take a look at one simple example. We are looking at what types of crystal. FCC means so-called face-centered cubic crystal, and we are looking at the so-called 111 plane. Okay, FCC and 111. That's so-called quite often the closed packed plane for the face-centered cubic crystal. And what does it look like? I kind of put it here, something like this. Closed pack. Just look at the solid circles. These represent the packing of atoms on this 111 plane. The atoms are arranged in this kind of hexagonal fashion throughout the plane, 111 plane, for a face-centered cubic structure. Okay, that's what you learned in undergraduate material engineering. And then the dashed one, let's say, okay, the atoms, let's say, on top of it. So if we define a term, epsilon, called a bond strength, if we define epsilon as our bond strength, then if one bond is broken, the energy of one bond connects how many atoms? Typically 2 atoms, right? One bond between typically 2 atoms. If one bond is broken, do you see that the energy for each of the atoms, right? One bond connects 2 atoms. When that bond is broken, each of the 2 atoms involved in that original bond would be, pay attention to what I write, raised by how much? Half of epsilon. Make sense? Again, what is epsilon? Epsilon is so-called bonding energy. And in order to break that bond, how much energy you have to spend? Epsilon, right? If you want to break that bond, you have to spend the epsilon. But based on energy conservation, where does that energy go? The one bond involves 2 atoms. You spend the epsilon to break that bond, but where does that epsilon energy go? That energy actually would cause each of those 2 atoms to raise by how much? Half of epsilon. Make sense? That's just your energy conservation, because initially these 2 atoms are bonded together. They have an energy, and you spend this epsilon of energy to what? To break the bond. And where does this energy go? Goes to each of those elements, and each of the elements will go higher a little bit because you spend energy. The system energy would go higher a little bit. And then we would say, okay, compare within the bulk. If we consider its atom on this so-called 111 types of crystal surface, which means the surface atoms are packed in this hexagonal packing, right? One has 6 neighbors in this plane. Every atom on this surface has lost how many so-called nearest neighbor compared with the bulk? I kind of draw it here. If I'm considering this solid atom in the center, the 3 dashed kind of circle represent what? Represent the 3 atoms if the center one where I'm pointing is still within the bulk, right? When you create a surface, you have to break bonds. Break how many bonds? Break 1, 2, 3 bonds of this atom to the 3 atoms that are touching it from the top. Make sense? That's what we say. I want you to read this sentence to yourself. For a individual atom on this so-called 111 type of crystal plane, if we have this surface, then this individual atom will have to break 3 bonds with the atoms that were originally above it in order to what? To create this surface of this 111. It's the same for if I'm pointing at this atom, right? If I'm looking at this atom on the surface, or if I'm looking another one on the surface, for each of these atoms on the so-called the 111 surface, 3 bonds have to be broken from what? From the atoms that were originally on top. Make sense? So then we can say for every surface atom on this 111 plane, they would lost 3 of its nearest neighbor. For the one in the center, it would lost this one, and this one. 3 of its nearest neighbor. And then the so-called excess energy. Excess energy for each of the 111 surface atom. Excess energy for each of these surface atoms, comparing with what? Comparing with when they are in the bulk, the so-called excess energy. Do you see that it would be 3 times of half of epsilon? Make sense? Again, what is epsilon? Bonding strength or bonding energy, right? When you break one bond, each of the atom got energy reached up by what? Half of epsilon. Now for this so-called 111 crystal, 111 surface, in order to create it, for any of these atoms, I have to break how many bonds? 3, because those 3 are on top. I have to break 3. So the excess energy compared with as if they are in the bulk would be 3 times of this half epsilon. Make sense? That's the so-called excess energy for each of the atom. Now let's think, how do we evaluate? How do we evaluate the so-called bonding energy? People have one way to evaluate the so-called bonding energy, which is related to the so-called sublimation energy. What is sublimation energy? What does sublimation mean? Sublimation means for the solid material to go directly into gas phase, right? For the solid material go directly into gas phase. And quite often for metal, this means going from bulk crystal into individual. I'm talking about typical solid metal material. For metal, when they are in gas phase, it's individual atoms. Unlike hydrogen, it's 2 hydrogen together, or oxygen, 2 oxygen together. But for metal gas phase vapor, it's just individual copper or individual titanium. Okay, so sublimation energy for a metal would be, if we call it LS. How much energy would it cost for 1 molar of single crystal titanium go directly into titanium vapor? Okay, if we call that is our sublimation energy. And let's say we are looking at what types of crystal? FCC, which means the so-called coordination number Cn. Cn for coordination number. What does coordination number mean? It means coordination number, the number of nearest neighbor atoms that are touching it. That's so-called coordination number. What you learn in material engineering, the basic introduction is, okay, for so-called FCC, that are totally 12 atoms are in direct contact with atoms of my interest. Okay, so with this information, Cn of 12, let's say FCC structure, if we know the so-called sublimation energy for this metal. Again, sublimation energy is the energy that you need for this material, this pure element metal, to go from solid FCC structure into individual atom gas. So now we would write something like this. Ls would equals to 12 times Na times half of epsilon. What is Na? Quite often, Na would be our so-called Avogadro number, right? Avogadro number, 6.02 times 10 to the power of 23. That's Avogadro number, okay? And this sublimation energy quite often means per mole of material, per mole of this metal, okay? Sublimation energy is 12 Na. Let's say we have Na for 1 molar. How many atoms do I have? Na, right? For 1 molar of this metal, I have Na number of atoms. And for each of atoms, how many neighbor does it lost? Once go from crystal to gas, individual gas, atom gas. 12, right? Because So this is what we have from previous slide, right? Excess energy, ESV, between the solid and vapor for this particular 111 plane is given by 3 times half of bonding strength. And from the relationship between sublimation energy and the bonding strength, we get this relationship, which is excess energy per surface atom on this 111 plane. Okay? And then, generally, as we mentioned, when we talk about the surface energy, we are typically talking about per unit area. Per unit area. Okay? And then, the gamma for surface energy per unit area, subscript 111 for the particular crystal plane that we are interested, would be ESV, the excess energy per atom times N111. What does N111 mean? It means the so-called number density. What density? Area density. Number area density on which plane? 111 plane. Okay? So this is okay. Theoretically, how we can get the so-called surface energy for this particular plane. Okay? And then let's look at the geometry a little bit. We are plotting only a section of the FCC 111 types of plane. 111, which means the hexagonal kind of close packing. 1 atom, 2 atom, 3 atom, 4 atom. Of course, there can be more. And the angles for these triangles are all 60 degree, right? Because we are talking about the same types of elements. Now let's look at this oblique parallelogram. You can kind of view it as two of triangles, right? Two of triangles. Each of the triangle would have equal edge lengths, and all these angles would be 60 degree. Okay, so let's this distance from the center of one atom to the edge would be the atom radius r. Okay, and then from this geometry we can calculate the n, which is atom number density per, not volume, per area. Okay, and clearly from what you learned in material engineering, this 2r would be square root of 2 over 2 times a. Last time we mentioned, what does a mean? A means the lattice parameter, lattice constant for these types of FCC crystal. Here I'm drawing the unit cell, a geometrical model kind of for the unit cell for a FCC crystal structure. Of course, well, I'm only drawing one unit cell, which means, okay, I'm only have half atom here, 1/8 of atom at the corner, right? At the corner. So A is the unit cell edge length, lattice parameter from one corner to the nearest neighboring corner. That's A. From here to here is also A. Okay, so at the surface for this cube, the surface diagonal from geometry point of view, you see that square root of 2 times A. Make sense? That's just the diagonal for a square. But from radius or from packing point of view, from one corner to the surface diagonal corner, that's how many radius? We would count 1. This is diameter, which is 2. Another one, totally 4. So you would see that 4r would equal to 4 times r would equals to square root of a, or put another way, 2r is square root of 2 divided by 2 times a. Okay, that's what you learn in materials engineering. So now let's look at within this so-called oblique parallelogram. Within here, we have one atom. Why one atom? We would count this portion, 1/6 of an atom. This portion, another 1/6. from here, 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 another 4 of 1, 6. So totally we have one atom within this, if you cut it, oblique parallelogram. And what is the area for this oblique parallelogram? It will be base times height, right? And what is the base? It's just from here to here is 2r. What's the height? From here, vertically down here. That's just the 2r times that sine 60 degree, which is square root of 3 times r. Make sense? And then, of course, mathematically we can combine. We are going to get this, and with the relationship between radius and lattice parameter, we can rewrite these equations. Make sense? And then we can, of course, simplify the mass, and the square root of 3 keeps down here, a squared keeps down here, and we would have 4 at the top. Okay? So this relationship gives us the so-called area density, number area density. It has a unit of number per meter square. Okay? And then as a result, the so-called surface energy for this FCC 111 plane would be gamma 111 would be E, the excess energy per atom, times how many atoms per unit area. And then when we plug the number in, the first term from this equation, the second n term from this equation, and if we combine, the 4 and 4 would cancel. We are going to have something like this, which means, okay, theoretically, if we know Ls, sublimation energy, if we somehow measure it by thermal experiment, if we can get A from X-ray diffraction or TEM, okay, we'll be able to theoretically predict or estimate the so-called surface energy if it's a single crystal exposing 111 plane. Okay? Let's pause here for a second.